All right, so today we're actually going to do some full circular motion review. We're going to cover everything that we've covered so far. This is going to serve as a really good prep for a quiz that we have coming up. So today's plan is going to be, again, we're going to recap everything we've covered thus far in this unit. It's going to include circular motion, vertical circular motion, bank curves, Kepler's Law, and satellite motion. Today needs to be hands-on. So in other words, I'm going to pose a question here. You're going to have to try it on your own or in a small grouping, and then we're going to go over it together. So we'll pause the video, and of course you'll go through the question on your own, and then we'll go over it together. What I'd like to see today is if you have like a separate color pen, so that when you finish doing the question the first time around, if you go over it with another color pen, so you can mark your own corrections, that'll let you know exactly where you might need to practice a little bit more. Now again, our quiz for this unit is coming up on Tuesday, November 19th. We're going to have the next class to prepare for this as well, so today is not going to be the only review day we have. We will have another day after this. All right, so the first question we're going to do here is on horizontal circular motion. Just pause the video so you can write this down and try it on your own. Okay, so we're going to go over this question now together. Papa John horizontally spins a circular pizza dough that has a diameter of 36.0 centimeters with a rotation rate of 180 RPMs. Remember, RPM stands for rotations per minute, and it's a measure of frequency. So part A is saying determine the speed of the outer edge of the pizza dough. Basically what that means is we need to be determining our VC, in other words, our centripetal velocity. And remember, VC has a couple different formulas here. You could get it out of your acceleration formula, or you could just use a standalone formula. The standalone formula is the one we're going to have to use here because we have a radius, or at least we could figure a radius given the diameter. Remember, radius is half a diameter, so you could tell the radius is 18.0 centimeters. Or in other words, in a more standard unit, we could say that's 0.18 meters. It's a decimal there. There you go. So we know a radius, and we know a frequency, and a frequency doesn't actually get used in any of the formulas that we've covered so far, but it can be turned into something called a period. And the reason, again, this is important, without me bouncing around too much here, we have VC is 2 times pi times the radius divided by the period. So again, if we could figure out what the period is, which is related to the frequency, right, we would be able to use this equation directly to solve for VC. Now, this frequency that it gave us, this 180 RPMs, that's kind of a bizarre unit for frequency. Generally speaking, we prefer a frequency in hertz. To change from RPMs to hertz, you just have to divide by 60. And this becomes a little easier to understand if you recognize that 1 hertz, or 1 hertz right there, yeah, 1 hertz is actually the same thing as saying 1 rotation per second, right? So if you have 180 rotations per minute, just dividing that by 60 will turn it into a rotation per second, which is more commonly known again as a hertz. So 180 RPMs, divide that by 60, and that pretty clearly becomes 3 hertz. Now, the other relation we have here is frequency can be connected back to period by understanding that period is just the reciprocal of frequency, so 1 over the frequency. So in this case, we would know our period is 1 over 3. And period, of course, when you use hertz for your frequency, period is going to be measured in seconds. So in other words, the amount of time it takes for a complete revolution of this pizza dough to happen, or to spin around, I should say, is 1/3 of a second. So we know from our VC formula, we're ultimately trying to find our centripetal velocity. We know, of course, what R is. It's 0.18 meters. And we know what T is. We just found it was 1/3 of a second. So all you have to do is just throw these numbers in now. So we have 2 times pi times 0.18 meters divided by our capital T period, which is 1/3. And throwing this into our calculator all in one go gives me VC equals 3.39 meters per second. And that is to the 3 sig digs that we would need for this question. Now, part B, determine the centripetal acceleration. Acceleration, or at least centripetal acceleration, is kind of weird because there was 2 formulas that were given to you on your formula sheet. There's one that says AC equals V squared over R, But then there's a longer one that says it's 4 pi squared r over t squared. Now, in this question, you could actually use either of those two formulas because we have velocity now, we have r, and we also have capital T, which is the period. So either of those formulas would work just fine, but certainly I think most of us would agree this formula is going to be a little quicker and easier to use. So there's nothing wrong with using this one. I guess technically this one would be more accurate, supposedly, but I guess when we're dealing with only 3 sigdigs in our question, it shouldn't make that big of a difference in the long run, but I leave it to you to try on your own if you wish. Bottom line is I'm going to use that shorter equation. AC is going to equal V squared, which will be 3.39 squared, divided by R, which is 0.18. Throwing this in my calculator takes 2 seconds. You get to 3 sigdigs, 0.638. And of course the units on this, because we put in standard units, we put in the meters per second, we put in meters, it should spit out an acceleration in meters per second squared. Okay, so this next question is a vertical circular motion question. Just pause the video here so you can copy the question down and give it a try. All right, so a 1.5 meter string will break if it experiences a tensional force of 200 newtons or more. If a 3 kilogram mass is tied to the string and whirled in a vertical circle, what is the maximum speed that this mass can be whirled without breaking the string? Well, I need to remind you, when we have vertical circular motion problems, so we have a circle, and something's being whirled around in the circle, our tensional force is actually going to be maximized at the bottom of the loop. Right? If you think back to those bucket of water questions, the bucket of water would be most likely to spill out at the top because that's because of the tensional force in the string holding that bucket of water in there is actually getting minimized up there. And it's the tensional force that actually contributes to the apparent weight of the water in the bucket. So again, the string we know will break if it has a tensional force of 200 newtons. And the place in this circle that's most likely for that string to experience a high force would be at the bottom. So I want you to think about the bottom of a circle in this case and what kind of forces are going to be acting upon this mass that was tied to the string. There's going to be a force towards the center of this circle that will be your tensional force, Ft. But there's also going to be a force pulling it straight down. That would be your force of gravity, Fg. Now in circular motion problems, we often consider that Fc is like our net force. And since Fc is acting as our net force, we just look at our free body diagram we just drew here and tell ourselves, okay, what is going in the same direction as your centripetal force? Those will be positive forces. And what's acting in the opposite direction? Well, centripetal force always points to the center of the circle. So we can say by our free body diagram right here that Ft is also pointing to the center of the circle. So we can say Ft is going to be our positive force. And we're going to subtract away our negative force, which would be the force of gravity. Now, Fc has a couple different formulas. Remember, Fc is just mass times AC, and AC has 2 different formulas, just like we discussed on the last slide. Now, in this question, because we're looking for a maximum speed, that's going to kind of cue us towards using that Fc formula that contains speed or velocity, okay? So we're going to say for Fc that the formula for that is mass times the centripetal acceleration, which is going to be v squared over r. So again, mass times centripetal acceleration, which is v squared over r. This is going to equal Ft. Ft is actually given to us in this question. So I'm not going to write it as Ft, I'm just going to write it as 200. And we're going to minus Fg. Now we can reasonably assume that this takes place on Earth, where gravity is 9.81 meters per second squared. So I can say this is just going to be m times little g, and we know little g for Earth at least is 9.81. Now let's throw in our numbers that we have here. Remember, we're trying to find maximum speed, so v is going to be left alone. M we know is 3 because it gave us the mass. So we have 3.00 times v squared over r, which is the length of the string in this case, so 1.5. And that's going to equal 200 minus the mass of the object, which again is 3.00, times gravity, which is 9.81. Multiplying this through, I'm going to leave the left-hand side alone for now. You could clean up the left-hand side if you wanted to, but I'm going to leave it pretty much the same. Might be a good idea to put brackets there. It's not really doing anything, but just looks neater as far as I'm concerned. 200 minus 3 times 9.81. If I put that in my calculator, I actually get 170.57. Now I'd like to get v squared all by itself. So to get v squared all by itself, just make sure that's more clear as a v. To get v squared all by itself, I'm going to times by 1.5 and then divide by 3 on both sides. And this is going to give me v squared equals 85.285. There you go. And of course, to find v now, we just have to square root both sides and then watch our sig digs. So v equals 9.23 meters per second. And again, I know it's in meters per second because I used standard units here. As long as you're using your standard units, that includes kilograms, that includes meters, that includes seconds, all of the standard units, you should be getting a standard unit as an answer. Okay, so next up we have a banked curve problem. Just jot this down and give it a try. So a banked curve on a highway is designed to allow cars to safely travel up to 120 kilometers an hour in frictionless conditions to make a 300-meter radius turn. What angle must this banked curve be sloped at in order to allow this? Now remember, banked curve questions from when we learned this a couple days ago, you always follow the exact same formula every single time. The only unfortunate thing is we don't give you the formula, you're going to have to remember it. This formula was tan theta equals v squared over RG. I'll leave it to you to figure out some sort of way to remember this. I was never able to find a good convincing way. I was never able to really think of anything creative to remember this by, but if you can, kudos to you. You do need to know what this formula is. We're not giving it to you. First things first though, we're looking for our angle, so we want to find this piece. We have a velocity, but the problem with this velocity is it's in kilometers an hour, so we'll want to change this before we go anywhere with this. We have a radius, and the radius is given to us in meters, so that's good. And then g, of course, is 9.81, which is always given to us. So first things first, we should go 120 and change 120 kilometers an hour into meters per second. Easiest way to do this is just to divide by 3.6, as we've been doing throughout the course. That's going to give you 33.333 repeating meters per second. Now that this is in a unit that's a little bit more convenient for us to use, we might as well plug it right into our equation. So we have tan theta equals 33.333 squared divided by r, which is 300, times by g, which is 9.81. This gives me tan theta equals kind of a messy decimal, but I'll keep as many decimal places as I can, 0.377,544. It's just what I rounded it to, so I kept 6 decimal places. It's more than enough. Now we'll take the inverse tan of both sides to get theta all by itself. So inverse tan is what's going to undo the tan here. So inverse tan both sides, and we get theta equals to 3 sig digs, 20.7 degrees. So the next question we're going to do is a Keplers Laws question. Just pause the video here so you can write this down and give it a try. Okay, so Mars has 2 very small moons, Phobos and Deimos. Phobos takes 7.65 hours to orbit around Mars at an average distance of 9,376 kilometers. Deimos takes 30.3 hours to orbit around Mars. What is the average distance between Mars and Deimos? Now, Kepler's law was another one that I don't give you the formula for. We often use Kepler's laws to figure out something called a Kepler's constant, which was a constant that was true for a certain object that things were orbiting around. You're not going to actually have to explicitly use the Kepler's constant here, but there was a formula associated with this, or rather I should say a ratio associated with this, that really helps us solve problems relating to several different things orbiting around a common object. The common object we're talking about here, the thing that's orbiting, or the thing that both of these things are orbiting around, is Mars. And since they're both orbiting around Mars, we can say the period squared of Phobos, so I'll put a p here, divided by the radius cubed of Phobos, and radius in this case meaning the orbital radius, not the actual radius of the moon itself, is equal to the orbital period squared of Deimos divided by the orbital radius cubed of Deimos. Now, since the question is asking us what is the average distance between Mars and Deimos, that means we're looking for this piece right here. All of the other information given to us in this question, like this many hours to orbit around Mars for Phobos, that would be your TP squared. And this one over here, the 9,376 kilometers, is the radius or orbital radius of Phobos, and we would just have to cube that. Likewise, this 30.3 hours would be the orbital period of Deimos, so we would just have to square that piece. Bottom line is just throw all of these numbers into this equation. So we can say for TP squared, we can say that's 7.65 squared divided by RP cubed. RP cubed is going to be 9,376 cubed. And in case you're wondering here, you don't actually have to care about your units as long as you're being consistent. I'm putting hours over kilometers. On the other side of this equal sign, I need to make sure I have hours over kilometers. And the good news is this piece was given to us in hours, and we don't know RD cubed, so we're just going to end up assuming or realizing that the answer will have to be in kilometers to keep things all even. So anyway, the time period for Deimos is 30.3. That's a 3 right there, 30.3, and we'll square it, divided by RD cubed. Now what I'm going to do, just to make my life a little easier here, is I'm going to rearrange this formula. I'd like to get this piece all by itself. So to do that, I'm going to multiply it over to the other side. And then, of course, I'll have to multiply this piece over here. And then I'll have to divide away this piece here. So it's going to be a whole switcheroo with these fractions. Some people called it like, cross multiply and divide. However you thought of this, whether you use cross multiply or divide, or whether you just analyze the fractions, it doesn't matter to me how you go about doing this, but we have to be able to rearrange this fraction so that we can get that RD cubed all by itself. Bottom line is, if we're getting RD cubed all by itself, it's going to be RD cubed equals 30.3 squared times by 9,376 cubed, all divided by 7.65 squared. And if you throw this in your calculator, you're going to get an absolutely huge number as an answer. RD cubed equals 1.293, and then a whole bunch of other numbers, but times 10 to the 13. And then, of course, we want to find the actual radius, which is going to tell us the average distance between Mars and Deimos. So we need to just cube root this. So cube rooting this is going to give us RD equals 2.35 times 10 to the 4. Now, before I wrap this question up, let's think about what our units are. Remember, since we had hours over kilometers equals to hours over an unknown, since it was hours over kilometers on the left side, we can assume it's hours over kilometers on the right side as well. So we can very safely say that this number is in kilometers. All right, here's the last question. It's on satellite motion. Just pause the video here so you can write this question down and give it a try. Okay, Sputnik 1 was the world's first artificial satellite. It was launched by the Soviet Union in October 1957 and emitted a radio signal. Sputnik 1 orbited Earth at an average altitude of 577 kilometers. Calculate in minutes how long it would take Sputnik 1 to orbit around Earth. So this is, of course, as the title even directly tells you, a satellite motion question. Satellite motion questions are going to work by saying that your centripetal force is equal to your gravitational force. Now, this was the kind of question that was really tricky because there were really strange algebra tricks that you had to perform in order to even solve these questions. The only number I've even given you here is the altitude. And remember, that's a very common trick. The altitude is actually just how far above Earth this object is. And in terms of an orbital radius, we actually need to find the distance from center to center. So we would still have to add the radius of the Earth to this whole mix. Anyway, before we get there, it's just something to keep in mind. Let's think about what our formulas are going to be here. We're looking for the time in minutes it takes Sputnik 1 to orbit around the Earth. The amount of time it takes for something to orbit around the Earth would be called the period, which of course is capital T. Now, the formula Fc equals Fg Capital T is never going to show up in the FG side of the formula, but it is potentially going to show up in the FC side of the formula. Remember, FC is just mass times your centripetal acceleration, and one of your centripetal acceleration formulas contains T. Let's use that one. Remember, it's mass times centripetal acceleration, which the one that contains T would be 4 pi squared r all over T squared. And this is going to equal Fg, which was G m1 m2 over r, over r squared. Now, we have a bunch of different masses here. On the left-hand side, we have this mass attached to the FC formula. This mass would be the mass of the satellite. So for all intents and purposes, I'll call it mass 1, which means mass 1 on the right side here is also the mass of the satellite. The FC formula uses the mass of whatever is orbiting the other object, right? Now, since m1 is on the top on both sides of these equations, we can actually cancel them out directly. So you do not even need to know what the mass of Sputnik was, because it's not relevant, because it'll cancel out in the math anyway. Another trick we can do, there's nothing else that's on the top on both of these or anything that's on the bottom of both of these, but r squared is on the bottom of the right-hand side. If we multiply that over to the left-hand side, it gets rid of it on the right side and turns the r right here into an r cubed, right? Because r times r squared would be r cubed. Then, of course, we want to get this t squared all by itself. So what I like doing is I like multiplying it to the other side and then dividing what was on the other side over to get t squared all by itself, which visually is going to look like 4 pi squared r cubed divided by g m2 equals t squared. Now, let's analyze what all these different variables are meaning. We're trying to find t. 4 and pi, of course, are just known, but r would be the orbital radius of Sputnik. We know the orbital altitude of Sputnik, but we don't know what that actual radius is. Well, first, let's turn 577 kilometers into meters, so that would be 577,000 meters. And let's add that to the orbital radius of the Earth. The orbital radius of the Earth is on your formula sheet. It's given as 6.37 times 10 to the 6 meters. Adding these together gives 6,947,000 right on the dot, and that would be your orbital radius. So we're going to use that number right there as our value of r. Now, as for the capital G down in this equation down here, the capital G is going to be universal gravitational constant. That's 6.67 times 10 to the negative 11. And this m2 is going to be the mass of the Earth, which is listed on your formula sheet as being 5.97 times 10 to the 24. Throwing all these numbers in here is going to give us, I'll just do it on this side over here, 4 pi squared, and then r, which is 6,947,000. And we're going to cube that and divide it by 6.67 times 10 to the negative 11 times by m2, the mass of the Earth, which is 5.97 times 10 to the 24. And remember, that whole thing still equals t squared. Typing this entire thing in my calculator, I'm very careful with it. I bracket the top and I bracket the bottom. The division piece just goes in the middle. This actually gives me quite a large number, 33,239,269.31. And that is t squared. Square rooting that is going to give me t. It tells me that 5,765.35 is t. But I think it's really important to recognize here, since we used standard units, t is actually going to come out in this one as being in seconds, the standard unit for time. We don't want it in seconds, though. The question was asking for it in minutes. So we have no choice here but to divide by 60 to turn it into minutes. So when you divide it by 60, that's going to be your final answer. So I'll make sure I round to the 3 sig-digs that the question was looking for. Dividing by 60 gives me 96.1 minutes. And that would be your final answer. So that's the end of the lesson today. For practice, I want to make sure that you've completed all of the previous handouts that I've provided to you. I'll also like to remind you that that quiz that's coming up on Tuesday is going to contain 5 multiple choice questions 3 numeric response questions, and 3 written response questions. And it's going to cover all the information that you see here on the screen. Pretty much everything that we've covered today is a really good indication of what you can expect on that actual quiz. So if you review the notes from today or rewatch this video, you should be in a better position for that quiz. And again, on Monday's class, we're going to have some more review, and we'll just make sure that we're understanding all this material. As always, if you're stuck with anything, please reach out, get some help from someone else. And if you need any additional help, feel free to send me an email or a message on Remind.